When Ephraim Shay bolted gears to a locomotive in 1880, railroad engineers called him a fool. Gears belonged on mill machinery, not locomotives. Everybody knew steam engines needed direct drive, pistons connected straight to wheels. That's how Stephenson built the rocket in 1829. And that's how every serious railroad operated for 50 years. Then Shays' clumsy, gear-driven contraption climbed a 45-degree logging track, hauling 50 tons of timber, while conventional locomotives sat useless at the bottom, unable to move past 4-degree grades. The locomotive that looked wrong, sounded wrong, and violated every principle of proper steam engineering became the most successful specialty locomotive in American history. Over 2,761 Shays rolled out of Lima Locomotive Works between 1880 and 1945. 65 years of continuous production. And today, more than a century after Ephraim Shay died, and his geared locomotives still run on tourist railroads, climbing grades that would destroy conventional engines in minutes. This is the story of how a logger with no formal engineering training solved a problem the railroad industry insisted was unsolvable, and why the machine everybody laughed at outlasted almost everything that came before it. But the problem started in Michigan's forests. The 1870s and 1880s saw explosive timber demand. Railroads expanding across America needed railroad ties by the millions. Construction boomed in cities from Chicago to San Francisco. Lumber prices climbed. Fortunes waited in Michigan's vast hardwood forests for anyone who could get the timber out. But Michigan's logging camps sat in terrain conventional railroads couldn't reach. Steep hillsides, sharp curves following creek beds and ridge lines. Grades that pitched 8, 10, sometimes 15% up narrow mountain valleys. And standard railroad engineering specified maximum grades of 2 to 3% on main lines. Even short-line railroads rarely exceeded 4%. The physics were unforgiving. A locomotive's drivers had to grip the rail. On steep grades, weight shifted backward. Drivers lost traction. Wheels spun. The train stalled. Logging companies tried everything. They built inclines with cables and stationary steam engines to winch logs up hillsides. Expensive, slow, limited capacity. They floated timber down rivers during spring floods. Seasonal, unpredictable. And logs got jammed in log jams that took weeks to clear. They used horses and oxen on skid roads. Labor-intensive, weather-dependent. None of these methods could move the tonnage railroads demanded at prices the market required. And the industry needed a locomotive that could handle logging railroad conditions. Tracks laid on ungraded roadbed following natural contours, curves sharp enough to make conventional locomotives derail, grades steep enough to make standard drive wheels slip. Railroad engineering said it was impossible. And the power required to climb steep grades exceeded what locomotives could deliver without losing traction. Making locomotives heavier for traction made them too heavy for temporary logging track. Increasing boiler pressure for more power made locomotives too expensive for short-line logging operations. Ephraim Shay wasn't a railroad engineer, he was a logger. He owned timber operations in Michigan. He faced the same problem every logging company faced: how to get timber from forest to sawmill economically. In 1877, Shay operated a small sawmill near Herring, Michigan, and he built a narrow-gauge tramway to bring logs from cutting sites to the mill. He tried conventional locomotives. They derailed on curves, slipped on grades, broke the light rail logging companies could afford to lay. Shay understood machinery. He'd built steam-powered equipment for his mill, and he knew gears could multiply torque. Mills used geared systems to power saws and conveyors. Why not a locomotive? The idea seemed absurd to anyone trained in railroad engineering. Gears added complexity, more parts to maintain, more things to break. Conventional wisdom said direct drive was simpler, was more reliable, more powerful. Shay ignored conventional wisdom. In 1880, he built his first geared locomotive in his own shop. The design violated every principle of accepted locomotive practice. Instead of horizontal cylinders driving the wheels directly, Shay mounted vertical cylinders on the right side of the boiler. The pistons drove a crankshaft running lengthwise along the locomotive's frame. The crankshaft connected through bevel gears to a drive shaft running under the locomotive. The drive shaft connected through more gears to every wheel on the locomotive, not just the drivers, but every wheel. And the result looked ungainly. Cylinders stuck out the side like a growth. The entire right side of the locomotive was covered in exposed gears and drive shaft. It looked like someone had bolted a sawmill's power transmission system onto a boiler on wheels. Railroad men who saw it laughed. Some called it a steam donkey, as others just called it ugly. Shay didn't care what it looked like. He cared whether it worked. The first tests proved the concept. The geared locomotive climbed grades conventional locomotives couldn't touch. On a 10% grade, steep enough to make standard locomotives spin their drivers and stall, the Shay pulled loaded log cars without slipping. The secret was mechanical advantage. The gears reduced speed but multiplied torque. At slow speeds, all of the locomotive's power went into pulling, not into maintaining momentum. But the flexible frame was equally important. Logging railroads couldn't afford graded, ballasted track. They laid rail on wooden ties directly on forest floors, following terrain contours. The track twisted, dipped, and curved. Conventional locomotives with rigid wheelbases derailed constantly. Our Shays design used trucks, pivoting assemblies of wheels that could follow track irregularities. The entire locomotive articulated, twisting to follow curves and vertical undulations that would bend conventional locomotives' frames. And because every wheel was geared, every wheel pulled. But conventional locomotives had only 4 or 6 drivers providing traction. The rest of the wheels just rode. Shay locomotives used every wheel for traction, spreading the locomotive's weight across more contact points and multiplying available pulling force. Word spread through Michigan's timber country. Other logging companies visited Shay's operation, and they saw the geared locomotive working where conventional locomotives failed. Orders came in. Shay couldn't build locomotives fast enough in his sawmill shop. In 1882, he licensed the design to Lima Machine Works in Lima, Ohio. Lima had experience building steam equipment. They refined Shay's design, from standardizing components and improving manufacturing processes. The first Lima-built Shay locomotives went to Michigan logging railroads in 1883. Testimonials flooded back. Logging superintendents reported the Shays handled grades up to 14%. They navigated curves as tight as 60 feet radius. Conventional locomotives required 200-foot minimum. They ran on rail weighing just 30 pounds per yard. Standard railroads used 60 to 90-pound rail. They pulled loads up grades that made conventional locomotives useless, but railroad engineers still dismissed them. The gear drive seemed like a compromise, something for specialty applications where real locomotives couldn't go. The mechanical complexity looked like a maintenance nightmare. All those gears, all that exposed machinery. Surely they broke down constantly. The vertical cylinders seemed inefficient compared to horizontal cylinders directly driving wheels. Then the numbers started coming in. Logging companies kept detailed records. They had to. Timber operations ran on thin margins. Every breakdown, every delay, every mechanical failure cost money. The data showed something unexpected. Shay locomotives were more reliable than conventional locomotives in logging service. And the gear drive distributed stress across multiple connection points instead of concentrating it in a few coupling rods. The vertical cylinders actually ran cooler than horizontal cylinders in hard service because condensation drained better. The exposed gears were easy to inspect and lubricate. No hidden wear points requiring major disassembly to check. Maintenance costs ran lower than conventional locomotives. Not because Shays were simpler, they weren't. Because they were designed for the application. Logging railroads operated in remote locations. And our Shays were designed for field maintenance. Most repairs could be done with basic tools. Replacement parts were standardized. Lima kept large inventories. A broken gear could be swapped in hours. A broken coupling rod on a conventional locomotive might require shipping the locomotive back to a shop. By 1890, Lima was building Shays for applications beyond logging. Mining railroads ordered them for steep mineral hauling routes. Quarry operations used them to move stone. Short-line railroads in mountain regions discovered Shays could handle terrain conventional locomotives couldn't. The ugly duckling was becoming indispensable. Production numbers told the story. In 1890, Lima built 26 Shays. In 1900, production hit 89 locomotives. By 1910, Shays were operating in every timber-producing state and in countries from Canada to Malaysia. And the locomotive that railroad engineers said violated fundamental principles was being built at higher rates than many conventional designs. The criticisms persisted. Shays were slow, top speed around 12 to 15 miles per hour compared to 40 to 60 for conventional locomotives. But speed didn't matter on logging railroads. And what mattered was pulling power at slow speeds on impossible terrain. Shays were noisy. The gear drive created a rhythmic clacking that conventional locomotives didn't have. But loggers didn't care about noise. They cared about moving timber. Shays looked awkward. All those external cylinders and gears seemed wrong. But appearance meant nothing if the locomotive did the job. Engineering journals finally started publishing technical analyses. Tests confirmed what logging companies already knew. On grades above 6%, Shays delivered more effective pulling power per pound of locomotive weight than any conventional design. The gear reduction gave them mechanical advantage. On tight curves, the articulated frame and all-wheel drive provided stability conventional locomotives couldn't match. On light, uneven track, the flexible suspension prevented derailments. Some engineers began to grudgingly admit Shay had been right. The gear drive wasn't a compromise, it was optimization for specific conditions. Not every locomotive needed to run 60 miles per hour on level main lines. Some needed to climb mountains, hauling maximum tonnage at walking speed. For that application, Shay's design was superior. Lima continued refining the design. By the 1920s, Shays came in 3 sizes: Class A for light industrial use, Class B for medium logging railroads, Class C for heavy hauling operations. The largest Class C Shays weighed over 160 tons and produced drawbar pull equivalent to locomotives twice their size on flat terrain. But on mountain grades, they outpulled everything. The peak came in 1929. Lima built 98 Shays that year. Then the Depression hit. Timber demand collapsed. Logging railroads shut down, orders dropped. Production fell to single digits through the 1930s. World War II brought a brief revival, military contracts for portable logging railroads in the Pacific Theater. Then dieselization ended steam locomotive production entirely. The last Shay left Lima in 1945. By then, 2,761 Shays had been built. 65 years of continuous production. Compare that to most locomotive designs. 5, 10, maybe 20 years of production before being superseded. The Shays' longevity proved its worth. It wasn't a specialty oddity. It was a mature technology perfectly suited to its application. Most were scrapped when logging operations closed or converted to diesel. And steam scrap was valuable during World War II and the post-war rebuilding period. Shays were cut up for steel, but enough survived to prove the design's endurance. Today, more than 100 Shay locomotives still exist. About a dozen operate regularly on tourist and heritage railroads. And these aren't museum pieces moved a few feet for demonstrations. They're working locomotives. Hauling passenger trains up grades diesel locomotives won't touch. The Cass Scenic Railroad in West Virginia operates 3 Shays daily on grades up to 11%. The locomotives are 80 to 100 years old, and they climb mountains every day hauling loads no modern tourist railroad would attempt with conventional power. The Roaring Camp Railroad in California runs a 1912 Shay up grades through redwood forests. Same grades that made the railroad build a Shay in 1912. The locomotive still does the job. Ephraim Shay died in 1916. He saw his design succeed. He saw it adopted worldwide. He saw railroad engineers who had called him a fool grudgingly admit his geared locomotive worked. He never had formal training in mechanical engineering or locomotive design. He just had a problem that needed solving, and the practical sense to ignore what everyone said was impossible. The locomotive that looked clumsy conquered mountains. The design that violated principles became an industry standard. The machine that railroad engineers laughed at outlasted almost everything they built. And sometimes the fool isn't the one trying something new. It's the expert so certain of conventional wisdom that they can't recognize genius when it's grinding up a mountain at 12 miles per hour. Gears clacking, pulling loads nobody said it could handle.